Hello and welcome to this video. I am very happy that you have chosen to spend some time listening to my video. My name is Hemant and I find machine learning and deep learning very interesting and have spent time learning and teaching machine learning and deep learning concepts. TensorFlow is probably the most mature and popular deep learning and machine learning library and a complete platform as well. TensorFlow also has a lot of support on all major clouds as well, including AWS, GCP, and Azure. Since I had some time to spare, I decided to explore TensorFlow from basics and note down whatever I find useful and fun, so that it becomes a quick revision guide for myself and you as well. I have kept the topics aligned to the TensorFlow developer certification guide as well. For now, I cover about 40 to 50% of the topics as per the certification guide, but I plan to keep adding to it in the near future. So let's quickly have a look at the topics that I'm going to cover, and that we can proceed with the rest of the presentation. So here is a list of the topics which I plan to cover in this series of videos. So the series is named as TensorFlow Basics with Hemant, and the session that we are recording just now is a session 1, and we are going to be talking about what is TensorFlow, TensorFlow versions, and their comparison and compatibility. We'll discuss about the TensorFlow 1 graph sensations concept. We'll also discuss constants and placeholders, and then finally we'll end with the topic of tensors, actually what the tensors are all about. Okay, but going forward we'll be covering more and more concepts. So in the session number 2 we'll be covering eager execution and how to combine eager execution and graphs. We will get introduced to the auto differentiation. Then in the subsequent session we'll be covering the concept of the modules, layers, and models, how to save and restore weights and graphs after training the model, and then what is the ML workflow, and we will take one simple end-to-end example just to illustrate how does it work. TensorBoard is a very important concept, so we will be dedicating one complete session to the TensorBoard. Then we will discuss the concept of the data pipelines. So how do we build the data pipelines for any sort of data so that we are able to feed data in a performant manner to the machine learning models. We will also discuss the TensorFlow datasets. There is a huge number of datasets which are made available by the TensorFlow. So what those datasets are, how we can utilize those. Then we will get into the TensorFlow TensorBoard profiler. So how do we profile the performance of the training, right? And then we'll get into the Keras API, and we'll discuss various concepts using Keras. So we'll start with the sequential model functional API, then model and its built-in methods. We'll discuss the callback, then the training method which is .fit, and then the training loop from scratch. So we'll get to see how to use gradient, and then we will get into input, like how to define the inputs for the Keras networks, and then we'll discuss activations, loss function optimizers, and various layers which are frequently being used. And then we will discuss about initializers, like how do we initialize the weights for all those different layers. We will also discuss some of the regularization techniques like dropout and the batch normalization. We'll also discuss pre-processing data augmentation layers. And then finally we will be also covering the TensorFlow serving, like how to deploy the models for the production purposes. And we will also cover the distributed training, like how do we train the models in the distributed manner. Okay, so that's the list of the topic that we are going to be covering into a series of videos. Okay, but for now let's get back to the presentation for this particular session. So this is where we had left. So let's go to the next slide. So before we really get into the discussion of the TensorFlow, etc., let's quickly differentiate between AI, ML, and deep learning. So you may have come across all these different terms, so machine learning, deep learning, and artificial intelligence many a times. So let's see what do these mean and how these are different from each other, right? So artificial intelligence is fundamentally mimicking any kind of human behavior in any form. Okay, so for example, playing a game, playing a game of chess, say for example, or say example jumping over the obstacle, or to have a conversation like we do, to recognize objects, or to be able to drive a car and more. So these are all the examples of the artificial intelligence. Okay, machine learning is about training a model on the input data consisting of well-defined features. So say for example, if you are trying to predict the price of a house, okay, so the features could be location of the house, number of bedrooms it has, whether it has a garage or not, and things like that. So those features are well defined. So using those features and the input data, actually we train the model, and once the model is trained, actually we get inferences from the previously unseen input data using that trained model, right? So that is the concept of the machine learning. In deep learning, there is no concept of a defined feature. So we do not define the features. The features are extracted from the input data, raw data. Say for example, if you have an image and we want to classify the image, so raw data in this particular case is the pixel, right? So image essentially has a pixel, there's a height of an image and a width of an image, and we have pixels in both the dimensions, and using the pixels, the features are extracted automatically during the training, and the correlation between those features is automatically learned during the training process, and then finally the trained model is able to classify the images. Say for example, classify the images of an animal or a plant or anything, the car or anything of that sort, right? So typically deep learning is implemented using artificial neural networks, right? So deep in the deep learning comes from the fact that artificial neural networks can have many layers, and these layers are made up of neurons, and we'll see what does an artificial neural network looks like. Okay, so let's get to the next topic here. So we are here, artificial neural network is fundamentally a supervised training algorithm. It basically can be used as a supervised training algorithm. And advantage of using artificial neural network over other ways of doing the supervised training is that it can learn complex nonlinear relationship between input data and the target or label values. So in this picture, as we can see here, we are feeding in the input data, and it has got the input features, it has got labels, and using this input data and the labels, actually we are training the network. So this is how the artificial neural network is going to look like. So it has got multiple layers. So it has got an input layer, it has got hidden layer, then it has got an output layer, and each one of the building blocks of these layers is actually the neuron. So each of these neurons, if you see, is going to look something. So this is kind of an exploded view of a neuron. So neuron will have multiple inputs, and the job of a neuron is basically to take all those inputs, multiply those by the weights that each of this connection has, and then basically add some bias to it. And then this combined output that we get actually is passed through an activation function. So activation function basically introduces us non-linearity, and we get an output here. So in the training process, what happens is ANN artificial neural network is trained by iterating over input data. It calculates the difference between the actual label and a predicted value, and it basically adjusts the weights in the response till most of the predicted values match the corresponding labels. So once the model is trained, so this is the built model, then we can use this particular model, give it a new data, and we can obtain a prediction out of it, right? So neural networks, because it can have multiple layers, multiple neurons, and it has a nonlinear element here. It can basically act as a function approximation. That means practically it can approximate any input and output relationship, and that's the beauty of the neural network, and that's the benefit of the neural network, because it can practically map any kind of input to any kind of output, because it can take care of any kind of non-linear relationship between the input data and the output data. Moving on, so far we discussed about the supervised learning and artificial neural networks. But there is also another architecture into which the artificial neural network fits in, and that is called as a generative network. Okay, generative adversarial networks. So in the GANs, as it is called as, what is being done is there are two components here. One is a generator model and another is a discriminator model. And typically, in this kind of an architecture, discriminator model is usually built using the artificial neural networks. Okay, so there are many applications of the GANs, and one of them, one very simple example to give, is essentially to generate say digital images. Let's say if you have digits 0 to 9, we can use GANs to automatically generate those digits. Okay, and we will see some of those more applications in the next couple of slides also. Before we move further, actually, let's also talk a little bit about the training process of the artificial neural networks. So artificial neural network needs to be trained on the input data before it is ready to do the predictions on the new data that we saw earlier. Now the training is actually split into two steps. One is a forward pass and another is a backward pass. Okay, so in the forward pass, what is going to happen is we are going to give a batch of input data to the model, and the loss between the predicted values and the labels is calculated in the forward pass. Okay, and in the backward pass, what happens is the derivatives of the loss with respect to the weights are calculated, and the weights are updated in the backward pass. Okay, and this whole process is called as a back propagation algorithm. Okay, so calculation of the derivatives uses the chain rule. So say for example, in this particular case, if you have to find the derivative of this particular output with respect to the weight which is in the innermost layer in this particular case, it will be basically built as a chain, the multiplication of various derivatives actually. So that's why this is called this is going to be using a chain rule. Okay, so as you can see clearly from this particular example is that the calculation of the derivatives, as there are like more and more layers, is a computationally very intense process. Okay, and that definitely means that we definitely need a lot of computing power when we are talking about training the neural networks. So just to get a feel of why we should be learning about deep learning and why should we even think about learning TensorFlow, let's take a look at some of the deep learning applications. Okay, so typically the deep learning applications are going to be split kind of bucketed or categorized into images and video, image and video processing, or natural language processing, or generative networks, and there are some other categories on their own also, like recommendations or fraud detection or the demand forecast, etc. Right? In the image and the video processing, you'll see that there are plenty of applications, right? So if you see from image classification to detecting certain entities into the image or the frame of a video. We can detect faces, we can detect text in the images, say for example, number plate detection, etc. We can moderate the content also, if the content is appropriate or not. If the content is not appropriate, kind of tell or create an alert out of it. Okay, we can also search a face, that means detect a face and match that face with the repository of the faces that we already might have. Okay, another category could be spotting product defects. So in a manufacturing process, if let's say if there is a vision model which is deployed onto a device, it can basically capture a continuous video and do this analysis if there is a particular product defect, and then it can take corrective action on it. In terms of natural language processing, some of the applications are which are like very popular. One of them is translation from one language to another. Transcription is like speech to text. So let's say if there is a medical transcription, you have a dialogue from a doctor, and then you convert it into some kind of a text automatically. Bots, that means we ask questions and automatic answering of those questions actually. Sentiment analysis, so social media and any kind of text bodies, we can do the sentiment analysis using the deep learning. We can classify the documents based on multiple things, say including the sentiment that the document has, or any other criteria that we might have. We can also generate the captions actually. So given an image, generate a caption for it, appropriate caption for it. Document summarization, so creating the summary of the documents, right? Now here comes a very interesting set of applications which are basically under the category generative, right? So style transfer. So style transfer is like, let's say there is a picture and we want to basically we want to see how that picture is going to look like if it was done by a some well-known artists. So we can use style transfer kind of networks for it. We can do the colorization of the images. So let's say if there is a black and white image, how will it look like in a color, right? And then adding sounds, say for example if there is a silent movie and there is a river flowing into that movie, how will it sound? So we can add sounds into the movie. We can do the image reconstruction. Let's say if the image is damaged, then it can be reconstructed from the rest of the image. We can also create super resolution images. That means let's say we have low resolution images, but then how will that image look like into the higher resolution? So we can extrapolate using the generative networks. Image synthesis, so generating totally new kind of images, right? So network will learn and then it'll try to generate something on its own. There have been attempts to compose the music also during the generative networks, using the generative networks. Couple of other categories, recommendations, so product recommendations. So if a customer is purchasing a particular product, what would you recommend him? Something that will go along with what he's trying to do, or from whatever he has done in the past. Okay. Fraud detections. So let's say there is a stream of transactions which is coming to you, detecting what kind of a specific transaction which looks fishy, that could be detected using the anomaly detection. Forecasting the demand. Let's say there is a power company and they want to see how the power is going to be for the next month and next month, etc., or any kind of a product demand actually that could be forecasted using the deep learning. So as you can see very clearly from the deep learning applications, that it basically covers a wide variety of application areas, and this is not the complete list, and the list is growing every day. So there's every sort of problem domain and application can be trained using the deep learning, and that's why deep learning is becoming very popular. Okay. Now it was realized that the deep learning can be used for variety of applications, but there were a couple of challenges actually. Okay, so as we saw, training of the deep learning networks or the artificial neural networks actually is a very computationally expensive process, right? So in order to train those models in the reasonable amount of time, something faster and parallel computation devices and paradigm was required actually. So this was actually taken care by the invention of the GPU's graphic processing unit, and the data could be kind of distributed onto those graphic processing unit. Each one of them will work on its piece of data, and then the results will be kind of collated. Okay. Now, second challenge was a specialized software framework. So we spoke about the concept of the neural network. So it has got like input layer and the hidden layers and the output layers, and then there is a process of giving the input to this particular network and then training it through a couple of iterations and then deploying that model. So this whole thing, whole workflow needs to be kind of encapsulated into some kind of a software library, right? And one more thing is all these processes of training and deployment prediction, they had to be basically spread across the multiple GPUs on a single server, or even GPUs on the multiple servers, right? So some kind of a software was definitely required to do all these different things, right? And that's where smartest people from Google Brain saw a big opportunity, and TensorFlow was born. Okay, so TensorFlow was born out of this need to have a specialized software which could do building of those networks, training those networks, deploying those networks, and other things like monitoring those networks when they were deployed, etc. Right, and it had to take care of the distribution of the computation across multiple GPUs on a single server or even multiple servers, right? And one good thing about TensorFlow is actually they were kind enough to make it open source, right? And that's what fueled the growth of the deep learning adoption by the industry, right? So as you can see, GPUs came in, and the TensorFlow actually supported this fueling of the application of the neural networks. Okay. So at present, if you see, TensorFlow spans this end-to-end machine learning workflow, so which includes processing of data, building and training models, evaluating those models, and then deploying those models, and finally monitoring the deployed models. Okay. It also enables deploying models on a variety of platforms, including servers, browsers, and mobile phones. So this is where that workflow, this is the axis where this is like a workflow dimension or axis, and this is the platform dimension, as you can see. So all the steps in the workflow, they are taken care by the TensorFlow and all the platforms. So whether it is a Python server or whether it is a browser or whether it is a device, that is all supported into the TensorFlow. And as I was telling you, TensorFlow is an open source library, so we don't have to pay anyone for using it. Extremely important. And as far as the production goes, actually, TensorFlow has come out with a TFX library. So that allows the automation of this end-to-end machine learning workflow for the production purposes. So for the development purposes, it's fine. We can manually do those steps. But when it comes to the production, starting from processing the input data to the inference, everything possibly needs to be automated, right? And that is where this TFX library fits in. Very big thing from the production perspective. Okay. We are not going to be getting too deep into the TFX, but just so that we know about it. So let's also see how did the TensorFlow versions evolve actually. So as you can see here, the pre-release of the TensorFlow was actually somewhere in the 2016 end, and then the final version 1.0.0 that was released in February 15, 2017. And then actually they had like various 1 dot versions, and then final version of the 1 dot series actually is 1.15.5, and that was actually released on January 6, 2021. Okay, and the version 2 of the TensorFlow actually came in into September 2019 actually, and today we have this version 2.4.1 which is the current latest actually, right? So how did the things change between the 1 and 2? So version 1 uses something called as a symbolic paradigm, right? So what does this symbolic paradigm means? So it means that the computation graph is created independently and then it is executed separately. So we create a graph first, computation graph first, and then we execute it in a session in version 1.x. Okay. In version 2.x, they basically came out with this imperative paradigm. So what is an imperative paradigm? Imperative paradigm is something like Python. You know, in Python we execute line by line, correct? So exactly the same thing. In the version 2, the execution of the program is line by line, and that is also known as an eager execution. Now, why eager execution? Because eager execution helps in during the development, because we can iterate faster. We can just execute a line and see what is going on. If there is something wrong, we can go and fix it, right? So why not just have imperative? Why was symbolic required? But symbolic is will basically using the symbolic paradigm, you can optimize the speed. Okay, so it will perform better, and it can be also ported to multiple platforms. So as you're seeing, whether it is a Python server or a browser or a mobile device, the graph is portable. Okay, so that is why both the things are good. Eager execution is good for the development purposes, and when it actually comes to the actual deployment or taking to the multiple devices, the symbolic paradigm or the graphs are important. And then there are ways to basically get both the best of both the worlds as well, and we'll see how that can be done. Now obviously there is going to be a question about 1.x and 2.x compatibility, right? So this is for the folks who have developed code in TensorFlow version 1 and now want to use it on the 2.x. So there are three things. There is a migrate utility which is provided, which is called as TF upgrade v2 utility. Now if you use that utility and give it a TensorFlow 1 code, it will convert it into a TensorFlow 2 code. But obviously it will not be able to convert everything. There are going to be a few issues, and if you feel that there are issues, you can basically fix those issues by using the compatible v1 compat module actually. So you can use this particular module and use with the minimal changes you will be able to execute the TensorFlow 1 code. Okay. And if you want to run the TensorFlow code as it is without any changes, what you can do is even with the 2.x, what you can do is actually you can disable the v2 behavior. Okay, you can completely disable the v2 behavior, so code will execute exactly as if it was 1.x code. Or you can also just disable the eager execution. So you can say that we do not want this eager execution. We just want the graph to be executed at once. Okay. So let's now step back a little and basically discuss a few concepts which are centered more around 1.x, but it's good to know those concepts even if you may or may not use them. The concept of the graph you are definitely going to use, but some of those concepts like placeholder etc. You may not use in the 2.x, but it is still good to know those concepts. Okay, so in the TensorFlow 1 version, there was a concept of this computation graph. Okay, and let's see how that graph is created and how it is executed. Okay, so graph, in this particular diagram you can see that this particular diagram, this is a graph actually which is representing this particular function x square into y plus y plus 2. Okay, so this is the output f, x and y. So how this is being executed? So there are multiple nodes here. Okay, so these blue circles, they are nodes, and as you can see there is a series of nodes, and each of this node is actually getting the input. Okay, so this particular node which is calculating say x square, we are giving this x twice as an input, and we are multiplying this. Okay, so there is a multiply operation. As you can see, a node is representing an operation here. So x multiplied by x, we are going to get an x square here. Okay, and then we are giving, so there's another node and we are giving this x square and y here. So x square into y, that is what is going to be the output of this, and then y we are giving to another node and we are adding this 2, so this y plus 2 part, and the output here is y plus 2, and the output here was x square into y, right? And we are adding those two things here, so this part and this part we are adding, and that is where we'll get our final output. Okay, so that is the concept of a graph. So essentially what we are doing here is there's a series of nodes. Each node has got an input, it has got an output. The input is a tensor, output is also a tensor, and don't worry about the word tensor, we are going to see what the tensor means actually. Okay, now how does it look like in terms of the code if you have to do this whole thing, right? So what we are doing here in this particular code is we are declaring two Python variables, and then we are we are basically having one TensorFlow operation here, and we are giving these two inputs here, a and b, and we are naming this operation of add as add here, and this produces another tensor which is called as c, and we are printing the c. Okay, now if we execute only this piece of code, it's not going to work. Okay, because we have just created a graph here. Okay, and we cannot execute the graph just by saying print c. Okay, so as we were discussing earlier, there's a separation between the creation of the graph and the execution of the graph. Okay, so the graph is executed in something called as session. Okay, so there is a library tf.session. So we create a session using this, and then we run this particular graph in a session.run. That's the method that's being used, and we give this particular name of the graph here, and we run this particular operation here. Okay, so that will execute this graph. So graph means it will basically look at, okay, I want C, then it will find out A and B, and then it will convert those into the tensors, and then it will create a third tensor by adding those A and B. Okay, this is another example of the similar thing. So here what is happening is we are executing basically a list of operations. Okay, those operations are defined using some other operations like tf.add or multiply or power and other things. So this is similar to this, just more like a little more number of operations here. Okay, There's a concept of a constants actually, and why that concept is required is because when we are giving the inputs as a Python variable or NumPy variables, they are going to be treated, they are going to be converted into the tensors, because the popular inputs like Python inputs or NumPy inputs, they are automatically converted to the tensors. But the catch is they will be given the TensorFlow names. Okay, so if we step back to the earlier slide over here, when this particular Python variable is being called here as a and b, they are going to be converted into tensors and they are automatically going to be named as something, okay, in TensorFlow. So that something may not be equal to a and b. Okay, so if you really want to give your own TensorFlow names and keep it consistent, then what you have to do is you have to basically use this call called as tf.constant. So what you can do is you can create a tensor out of a scalar or any kind of input, and you can give it a name, and this name will be a TensorFlow name. Okay, that means you can refer to this particular thing using this particular name over here. Okay, so we basically if we are trying to do the same thing that we did in the earlier slide, what we do is we create two TF constants and then we add them and we give it a name. Okay, and then we can do the computation as we did earlier. Okay, these are few more examples of how to create constant out of scalar. So scalar is basically a single value. Okay, so 2.3 in this particular case, and we can also give it a data type, so we can create the scalar value of different types. Okay, now here is another example, right? So we can also create a matrix out of a list of the values. So there are two lists here, so one list is 1 comma 2, another list is 3 comma 4, and actually we are creating a list of the list, and we are creating a TF constant out of it, and what we are going to get out of this is we will get a matrix. Okay, and we will discuss about a couple of attributes of this particular matrix as we go further. But just to recap, the constants are fundamentally used so that to maintain the consistency between the naming of the variables in the TensorFlow. There's also a concept, and this concept is mainly for the version 1. So there's something called a placeholder, and this particular concept actually came in because we may not know the shape of the data till the runtime, so we may not know the batch size, etc., of the input, and that is where we require some kind of a placeholder to be declared, and we should be able to bind the input data at the runtime using this particular placeholder. So if you really see this particular statement here, so there is a constant defined which has got a shape of 3, and so this is a vector of 3 values, and then we are declaring a placeholder which is also of the shape of 3. Okay, and we are adding these two together. Okay, so this we have declared as a placeholder. That means we do not know the values until the runtime. Okay, so what we do here is we create a session, then we create a dictionary. Okay, and we say that this placeholder is this b needs to be replaced with this list 1 comma 2 comma 3. Okay, and then how do we feed it actually? So we say that so now here we are running the session, and we are saying that okay, this is my graph, and then my feed dictionary is equal to d. So I am giving this definition. So what it is going to do, it is going to replace b by this particular value. So b is going to be replaced by this, so it's going to add up a and b. Okay, a and b addition, and the data is going to be 1 to 3. Okay, vector of 1 to 3. This is another example how we can create a placeholder. So as I was mentioning earlier, Sometimes we may not know the particular dimension of a input, so we can declare it as none actually. So let's say there is a network and we want to basically give a series of batches of images to that particular network, and the shape of those pixels is 784, like 28 by 28 image, say for example, but we do not know like how many images we are going to give, so that's why this is declared as none here. Okay, so this is another example of a placeholder. Okay, now we discussed about the session graph and placeholders, right? Now we talked about tensors flowing through a graph and also placeholder which accepts input data into the first operation, right? Now data that flows through is represented as tensors. Okay, we do not want the data to change, hence tensors are immutable. Okay, also the data can come in many shapes, so tensors are multi-dimensional arrays of any shape. Okay, so the data could be a single number, as you can see here, so which is a scalar. Okay, single number, it has basically no shape. Okay, now it could be a vector. It could have say for example 3 values, 5 values, 10 values, 100, whatever it could be. Okay, so it has got a one-dimensional shape here. We can also have a two-dimensional data. Okay, so it is going to be like a dimension of height, dimension of width. So images, for that matter, they are going to look like the matrix, because say images typically have like a width and height, right? So they are represented as number of pixels and they have the dimension of a matrix, right? Now what could be a three-dimensional matrix? So once again, a colored image could be a three-dimensional tensor. So this is a basically say if you are basically RGB, if you are trying to think an image, this could be a red, this could be green, this could be blue pixels, right? So that is why the different dimensional arrays, the multi-dimensional arrays are required to hold different kind of data. Okay, let's also discuss some of the attributes of the tensor. So some of the attributes are shape. So shape is actually in this particular case, the shape is 3. Like how many elements are there on each of these axes? Here we have like 3 elements in this axis, 2 elements on this axis. The shape is 3 by 2 in this particular case. Rank is like how many dimensions it has. So in this particular there is 0 dimension. In this particular case there is 1 dimension. In this particular case there are 2 dimensions here. Okay, and the size, that is a total. So in this particular case it is 3 into 2. So 6 is basically the size of the matrix in this particular case. In this particular case it will be 3 into 2 into 5. So 10 into 3, 30. That will be the size of the matrix actually. So that's a property of the tensor. Okay. So how do we create these tensors? So we can create a rank 0 tensor using something like tf.constant, and we can just give the value. If you want a rank 1 tensor, we can create it using a list of the values. In this particular case we are giving the 3 values. Matrix or a two-dimensional tensor we can create using a list of the lists. So 1, 2, 3, 4, 5, 6, and we can also define the data types. Now rank 4 tensor, so we are basically initializing a 4-dimensional tensor, and these are the dimensions 3 into 2 into 4 into 5. Okay, we can use the TF1s also or TF0s. We can also get a tensor using the range. So we can give a starting value and the limit value and a delta. That delta, that means, say for example, if you are going from 1 to 6, It will start with 1 and then it will go to 3 and things like that. It will skip by 1 if the delta is 1, or if the delta is 2 it will skip by 2 and things like that. Okay, so these are the different ways we can create the tensors. Okay, now once the tensors are created, what do we do with them, right? And that is where some of the discussion that we had earlier, that machine learning needs basically a lot of computations during the forward pass and the backward pass actually comes in, right? So we build essentially the operations to create a computation graph, and we will see that this matrix multiplication additions are very heavily used during the forward pass, and update of the gradients etc. that is being done in the backward pass. So all these calculations, they are being done using the tensors and the related operations over there. Yeah. Now what is the concept of a tensor indexing and the slicing, right? So indexing is all about getting to a specific element of the tensor. Say for example, here we have an one-dimensional tensor here. So how do we get the first value? So we say that rank 1 tensor. So this is where we have created the tensor, and then we can access it using 0.numpy value. Okay, so it will basically give us the 0. We can also start backwards. So the indexes, negative indexes, count backwards from the end, and we can also do the slicing using start, stop and step. Okay, so these are the different ways we can get to the elements. Okay, and we will see these concepts a little more closely when we actually get into the Google Collaboratory notebooks. Okay, we can also do the reshaping of the tensors, right? So when the data actually comes from the external source, it may not be exactly in the form that is required to be fed to the neural network, and that is where the reshaping actually comes in. Okay, so the constraint on the reshaping is that the total number of elements. So in this particular case, let's say we have 3 into 2 6 into 5 30. The reshaping also should maintain the total number of elements into 30. So we can reshape it to, like, something like 3.3 multiplied by 10 or 6 into 5. That is all fine. Okay, because the number of elements here and here and here, they're all the same. Okay, we are just we are trying to reorganize the tensor values into a different shape. So far actually we have been talking about the tensors which are uniform. Okay, so that means in the previous slide, all these tensors, they had like on a particular axis, they were all similar number of elements. Okay, but we can have the different elements onto a specific axis, and that is what is called as a ragged tensor actually. So this is how it can be created, by giving lists of the different lengths. Okay, and this is created using tf.ragged.constant, and we give this list over here as an input here. We can also create the string tensors. Now string tensors, once again it is given as a list here. Each one of the string has got different number of characters, and if you see the final shape of this particular operation over here, you will see that it is 3 comma. Okay, so it means that it doesn't worry about how many characters you had into each one of those strings. You will not be able to access individual elements of this particular string. Okay, the shape that you are going to get is, okay, it is created as basically a tensor of 3 strings here, and they are basically stored as a byte strings. There is also a concept of a sparse tensor, right? So if you see the sparse tensor, how the values are stored here. So at the index 0 0, this value 1 is stored here, and this is a value. At the index 1 and 2, so first row and second place, you are storing 2 here, so that is being written as here. And now if we give the dense shape as 3 by 4, what we are going to get is this tensor, which is called as a sparse tensor, right? Sparse means the remaining places. So these were the remaining places, right? All these empty places, they are going to be filled with zeros here, and that is why it is called as a sparse tensor. So this is just for our information knowledge purpose, because these kind of tensors could be used in certain places, so we should be aware that these type of tensors also exist actually. Okay, so before we go to the next slide actually, which is more like a session summary, and I'll display it for you. Before we actually go to the session summary, what we'll do is we'll also open the notebooks, and we will see we'll see these concepts in practice actually. Okay, so let's open the first notebook. So the first concept that we discussed was about the sessions and the graphs and the constants. So those of you who are not familiar, this is a Google Collaboratory notebook. So Google Collaboratory notebook actually is, first of all, it's a free of cost. You can use your Gmail account to log into the Google Collaboratory, and you can create those notebooks. Okay, and there's a choice of the runtimes that you can have. So you can have either no hardware accelerator, or you can use the GPUs or the TPUs here. Okay, so for now I have not chosen any accelerator over here. And when this particular notebook, when you create a notebook, the Google Collaboratory at the back end, it will automatically create a kind of a server for you, and your notebook is going to be executed on it. And by default, the version of the TensorFlow that is going to be installed, and many other libraries which are automatically installed. So version that you get the latest version 2.4.1. okay, but there are ways to override that also. You can choose whatever version of the TensorFlow that you want to run onto the Google Collaboratory, and we will see how that is being done. Okay, so since we actually wanted to start with the TensorFlow 1 and explore a few concepts of graph, session and constants, what I did was actually I installed this version of TensorFlow 1.14. okay, so by default the version of the TensorFlow is going to be 2.4.1, but I am actually going and installing a TensorFlow version 1.14 over here. Okay, so let's go and execute this. So the objective of this particular notebook is actually demonstrate some of those concepts which we discussed about creating a graph and run that graph using the session, and also the concept of the TensorFlow. Okay, let me see what is going wrong here. Okay, I think there was some kind of a typo here. Let's delete this part, save this. Let me do the Control S so that I have saved. Oh, once again I did another typo. Control S, so I've saved my notebook. It's executed. This time it should go through. Yes, so it is picking up the TensorFlow version 1.14. By the way, I simply love this Google Collaboratory concept, because this is allowed the developers to experiment free of cost and learn as much as you need to, okay, or want to. So it's a fantastic concept that Google has given us. So as you can see here, the default TensorFlow version 2.4.1 has been uninstalled, and then we are going to be getting this 1.4. So it is installing a few more, uninstalling a few more things. So that's fine. We are done with this now. Okay. Now we can import the TensorFlow. So we imported the TensorFlow, and now is the time to try out a few things. Okay. So the first example that we had seen, this is a Python variable. A and B are Python variable. We are just doing a simple operation here and printing a C. Let's try to see what happens here. So what happened? Nothing actually. We did not get a value of C because this graph was not executed. Okay, the graph was created, but it was not executed. Okay, so let's try to execute it in a session. And there we go. We got the value 5, which is addition of 2 and 3 in this particular case, right? So we created a session and we executed the graph into that particular session. So the same thing can be done a little more easily with this particular syntax also, with tf.session as session and then run the session is going to give the same result, right? And the same concept here, that we can basically name the variables in the TensorFlow as we like to by using the concept of a tf constant, right? So we are trying to do the same thing, but we are replacing the Python variables with the tf constants here. Okay. And a few more examples, like we are trying to execute the scalar and matrix here. So as you can see here, there are basically 2 rows and 2 columns here. 2 by 2 matrix has been created. So this was a result of this operation. 2 by 3 was a result of the first operation. Now here is the concept of a placeholder. Okay, so we have this A here, which is defined as 555, and then we are binding this data 1 2 3, and then we are adding up these two values. So 5 plus 1 6, 5 plus 2 7, 5 plus 3 8. So that's the result that we get. So we are executing this part, right? Now just to give you a more concrete example of all these the tensors and the placeholders and the operations together, what we'll try to do is we'll try to build a operation. So we'll multiply the weight matrix by the input, and then we'll add a bias to it. So there is a matrix multiplication operation, add operation, and activation operation. Okay, 3 things. So what does this mean actually? What we need to do is we need to feed B some batch of images of 784 into a network, right? So what we need is actually a placeholder of B into 784. Okay, so B we do not know, so that is why it is going to be defined as none 784. Okay, and we want to initialize the weights randomly. So we are doing doing that using a normal distribution with a 0 mean and a standard deviation, and biases are initialized as small constant values as zeros. That is what is happening, and the input is 784 and we have 200 hidden units. So the weight matrix is going to be 784 into 200. Okay, and 200 biases are going to be required, one for each hidden unit. Okay, so let's see how does this look like. So we define a placeholder with a shape of none and the 784. This is the initializer. So we initializing this, we are going to use to initialize the weights, and we create a W using a get variable call. okay, of this particular shape, 784 into 200, and this is where we call that weight initializer. Okay, weight in it, and then we create a graph here, and the same thing we do for the bias also. There's a bias initializer, and we create a bias variable, and then we build a list of the operations, right? So we start with the matrix multiplication, we multiply the input by weight, and then we add the bias to it, and then we pass it through the activation. Okay, and here is an operation to initialize everything. So when we call this tf.global variable initializer, everything is going to be initialized, all these parts are going to get executed, and then we run the session. Okay, so we create a data here of 100 into 784. Okay, because we want to create 100 samples of 784, and then we are feeding it through the placeholder. So this feed dictionary we had created here, which was X was mapped to this particular data, and then we are passing this as a feed dictionary. Okay, so let's execute this part. So that's it. Finally we printed this particular H. Okay, so H was this the final output of all this graph actually, and that's what we got over here. Okay, so that's pretty much everything that we wanted to see in the first notebook. Let's go to the second notebook, which is more about the tensors. Okay, so here now we are going to be using the default Tensorflow runtime, which is 2.4.1. so we can directly import the TensorFlow here, and we are also importing the NumPy. Now we are defining some of these tensors here. So we have this one dimensional, and x2 is a like a two-dimensional matrix, and we'll see the difference between x1 and x2 here when we print it. Okay, and then we are also trying to create another tensor through tf.1s and tf.0s and tf.range, some of the mechanisms that we discussed earlier, and we are just trying to print all this. So as you can see here, x1 it is 1 2 3 4 5. Now notice the shape, it is 5 comma, that means it is basically a vector, okay, of 5 values, and the data type is integer 32. So we did not give any data type here, so by default it took 32. Okay, the second one, there was a minor difference actually. We had put one more set of brackets here, so it is a list within the list. Okay, and let's see the shape of that. The shape of that is 1 comma 5. What does it mean? Basically it's a one row of 5 values, that is what it means. Okay, and once again the data type is integer 32. So another one, tf.1s that we created, 1 and 5. So one row 5 columns, one row 5 columns, shape of 1.5, 1 comma 5. Same thing here, tensor of zeros and tensor of a range. So range we started with 1, limit is 6, so 1 to 5. So shape is 5 because there are 5 elements, and data type is 32, and because the delta was 1, so that's why it is in the step of 1. If we change this to 2, we'll see what happens. Just re-execute the whole thing. So you see that it basically skipped 2 and 4, 1 3 5, and you got a shape of 3 here. Let's talk about some of the attributes. So you remember we had talked about shape, size, and the rank. So we'll try to see what those things are. So let's create a rank 0 tensor here. So we are just giving a single constant here, and we are getting this x size we are printing the rank here, shape here, size here, and data type here. Let's do this. So what we are getting is a shape of, it's a dimension 0 dimension, shape no shape, size is 1 value, data type is 32. So that was our rank 0 tensor. Okay, let's try to create a rank 1 tensor. So it is 5, 6, 7, 8. We are giving 4 values here. So what we get? So we get dimension as 1 dimension, 4 comma 4 elements here, size is 4 elements, and the data type. Now we are giving basically a list of lists here. Okay, so we are expecting a matrix here. So 2 dimensions, right? Width and height, and 2 by 3. So we have the 2 rows, 3 columns. Total elements is 2 into 3, which is 6. Okay, as you can see here, I am also printing the tensor here. So you are seeing here, first row and the second row, 5, 6, 7, 7, 8, 9, and the shape of 2 by 3. So 2 rows, 3 columns. So this is the third dimensional array. Now look at the list actually. So we have this outer list, and then we have these 2 inner lists, which are also consisting of 2 inner lists, right? So basically is going to be, so bigger elements, if you say 2, and then we have 2 and 3, 2 into 2 into 3. So dimensions 3, and then 2 into 2 into 3, that's the shape, and this is how it looks like. Okay, now the concept of the indexing and slicing, actually, that's what so once again, to recap, indexes start at 0. Negative indexing is like starts, you can give something like -1, -2, and things like that. And then for the slicing, you can use start, stop, and the delta, start, stop, delta over here, right? So this is a one-dimensional array, and let's see how does it look like in the first place. So we are trying to access the first element here. Okay, and start at 0, last element, so we are trying to get the -1 from the backward, we are counting backwards, and then in between first and the last, that's what we will try to do. So start with 0 and end with -1, that's what it means. So first element obviously 0, last element 11, and everything in between 0 and 10. So just mind it is up to 10, it has not included 11, just remember that. Okay, so this is the indexing of the rank 2 tensors. How do we index the rank 2 tensors, right? So let's create this level 2 tensor in the first place. This is how it is looking like. The shape is 2 by 6. First element of the first level. So when we are trying to do 0, it's going to give me this whole row here. That is the first element. Second element, so I count, this whole thing is 0, this whole thing is 1, 0 and 1. Now if you want to go within this, then that is where you use this comma. So you can say 1 0, that means something like 6 over here. Okay, and 1 2, so 0 1, 0 1 2, that is 8 over here. Okay, so just let's execute this part. There you go. So everything as we expected. These are some of the operations that we have to know. We can do any kind of operations: element wise multiplication, matrix multiplication, finding maximum minimum, index of the maximum element, computing soft max values. All these different operations, they can be conducted. So let's start with some of the basic operations like addition, multiplication, etc. So we are creating these two things here, and then we add up these two things. Okay, so 2 plus 1, 6 plus 5, like that. Okay, so this is element wise addition it has done. This is a multiplication, so this is a normal multiplication, 1 into 2, element wise multiplication, 6 into 5 is 30 and all, right? Then we can do the matrix multiplications also. So this has got a different result than your element wise multiplication. You can also do the reduction operation also. Okay, so we had this this was our matrix, right? So what is the maximum value in this whole thing? The maximum value is 9 here, right, out of the 2. So if you do the reduction operation, we should be able to get those value maximum. And what is the maximum, the index of the maximum value? That is going to be printed using the argmax, which is 1 and 1. Okay, so let me just scroll up here. So it was 1 and 1. So this was my 1 and 1. 0 and 1. Let's execute this part. And then the softmax. So softmax is actually you give a vector and it basically gives a list of probabilities, and the sum of all those probabilities is 0 actually. Sum of the probability is 1, right? So for each of the row, if you see this 0.11 plus 0.88, 0.017 plus 0.98 and all, they will all add up to 1. And this is about the reshaping actually. So we created this 6 comma 1 comma 6, and then we reshaped it into different shapes like 6.1 or 3.2. So let's see how does that look like. So this was a dot shape of the initial tensor is 1.6, shape of the first reshaped tensor. So we reshaped it into 6 and 1, so we got 6 and 1. Okay, third is 3 and 2, so we got 3 and 2 here. And then if you want to totally flatten, then you basically give reshape as -1, so it gives you 6 comma. So it is flattened, actually it is removed this particular dimension of 1 here. So that's pretty much about the reshaping actually. Okay, and then the broadcasting. So if what is happening here is there's a size mismatch in the two tensors here. One is of the shape of 5 and this is of a different shape, but when we multiply actually this is going to be expanded to the size of the bigger tensor actually, and it will multiply each one of these element with a 5. That's why you will get 5 into 1, 5 into 2, 5 into 3, 5 into 4. So that is called as broadcasting actually. And then these are some of the examples of how you create the ranked tensors and the string tensor and the sparse tensors. So we are creating a ranked list here, and then we are calling this tf.ranked.constant here. And as you can see, final tensor which is created is of different shapes here. So similarly, this is how you create a string tensor. So as you can see, this is a byte code actually. Each one of this string is a byte code. And then the sparse tensor. So as you can see here. So we had this value 0, 0 at the place index 0, 0. We have this value 25, and then at 2, 2. So 2 and 2, 50, and 4 and 4, 100. That is how your sparse tensor is going to look like. So it's going to fill everything with zeros actually. Okay, so that's pretty much in terms of the notebooks for this particular session. Let's come back to the summary of this particular session on the let me come to the summary quickly. Well, this is the summary. Actually, we started with the TensorFlow, and we understood that it is a key machine learning and deep learning library and a complete platform. The latest version is 2.4.1, and the last 1.x version is 1.15.5. 2x actually allows us imperative programming in addition to the symbolic programming. 2x has easy to use high level Keras API. In 1.x, we can create graphs and run in sessions. 2.x, it is not required. In 1.x, placeholder is used to bind data at the runtime. In 2.x, you don't need it. Constants allow us to create tensors from Python or NumPy data types, and the names are consistent. And then we represent data as tensors. Data could be of different shapes, so tensors also could be of different shapes and can have multiple dimensions. They also have the attribute which is like shape, size, dimension, rank, and we can create computation graph using operations, and we can access tensor element through the indexes, and we can reshape tensors. That's pretty much we learned in the session 1. I hope you will find this useful, and subsequently I'll be recording the other sessions, and I'll be uploading it onto the YouTube. So thank you once again for listening to this video, and if you have any comments, please you can put it in the comments in the YouTube or on the LinkedIn. Thank you so much. Bye bye.